Okay, so this is a demonstration of something called a Newton's cradle. Okay, and there's a lot of different types of these, and this is kind of a typical one. This has 5 equal mass balls hanging from fishing wire. Okay, and so each one acts independently like a pendulum. Okay, except there are 2 wires. And what I'm going to do is I'm going to demonstrate this, and what this demonstrates is what would be called a more or less elastic collision. This is what's called a nearly elastic collision. Okay? And what I'll tell you what the answer is before we go there, and then I'll come back to it. In a nearly elastic collision, both the momentum is going to be conserved and the kinetic energy will be conserved. Okay? Now there's friction acting in this Newton's cradle. So this Newton's cradle doesn't move indefinitely, but it will go for a few seconds until friction overcomes the motion of the balls. Okay? So first we're going to move one ball. Okay? So when I raise this ball, I'm adding potential energy to it, right? And I'm going to let it go, and it's going to swing down, and that potential energy is going to be switched to kinetic energy. And it's going to strike this ball, and this ball will strike with some momentum, and that's going to be a function of the mass of the ball times the velocity of the strike. Okay? And that energy is going to be transmitted through the hanging balls, the 4 hanging balls, and elastically, or nearly elastically, okay? And so when it reaches the last ball, it basically that ball has to move, and it will come out with about the same velocity, or if there was no friction, it would come out with the same velocity as the ball going in. Okay? And it has the same mass, obviously, right? So it would have the same momentum. So let's just show that really does happen. So I give this potential energy, I convert it to kinetic by dropping it, and you can see the ball striking the opposite side. Okay? And you can see it coming out. And you notice the velocity of the 2 balls is very comparable. Now I'm going to do it again. Notice the velocity of the 2 balls as they swing. Okay? The velocity of the 2 balls is very comparable. Okay? So the momentum is conserved. Okay? Same mass, same velocity. Okay? Now I'm going to do 2 balls. Well, by doing 2 balls, I'm increasing my mass. My velocity is going to be a little bit different, but kind of the same. So I'm going to drop these 2 balls. You'll notice that mass, because momentum is conserved, the mass on the opposite, as the balls come out the other side, has to be the same. So how many balls do you think are going to come out the other side? 2. Okay, so 2 balls go in. I'm going to do that again. Okay, 2 balls go in, and 2 balls pop out. Okay, momentum's conserved. Okay, now let's try a kind of a clever thing here. We have 3 balls. Well, this is an odd number of balls. There's 5. So if I pull back 3, how many balls are going to come out the opposite side? Well, if momentum is conserved, 3 should come out the other side. Okay, so let's find out. So again, 3 on each side, and 2 balls get left behind in the middle. Okay, and I'll do that again so you can see that better. Okay, 3 on each side. Okay, so as I've said, momentum is conserved. In addition to that, because this is a nearly elastic collision, kinetic energy is also conserved. So the kinetic energy is the mass times the 1/2 the mass times the velocity squared of the ball. Okay, so when I let this go, okay, kinetic energy is also conserved because one mass, just like the mass going in, will come out, and the velocity will be the same. So kinetic energy is also conserved. Okay, and if I do 2, again, 2 balls will come out. Kinetic energy is also conserved. Okay, because these 2 balls will come out. These 2 balls will come out at the same velocity as the 2 balls going in. So kinetic energy is conserved too. Okay? Okay, so that's it.